Hi everyone! Today, we're diving into the fascinating world of electronic filters. Specifically, we'll explore the transfer function of a third-order high-pass filter. Understanding this mathematical expression is key to designing and analyzing circuits that process signals. It tells us exactly how a filter will behave across different frequencies. First, what is a high-pass filter? Imagine you have an audio signal. It contains both low-pitched sounds, low frequencies, and high-pitched sounds, high frequencies. A high-pass filter allows the high frequencies to pass through almost untouched. It blocks or significantly reduces the low frequencies. Think of it like a sieve for frequencies. Only the fine, high-frequency particles get through. Now, what about third order? The order of a filter tells us how steeply it can cut off unwanted frequencies. A first-order filter has a gentle slope. A second-order filter has a steeper slope. A third-order filter has an even steeper slope, making it much more effective at separating frequencies. It uses three reactive components, like capacitors or inductors, in its design. This gives it a more aggressive roll-off characteristic. The transfer function is a powerful mathematical tool. We represent it as Hs. It's a ratio of polynomials in S, where S is the complex frequency variable, S equals j omega, with j being the imaginary unit and omega being the angular frequency. For a third-order high-pass filter, a common form of its transfer function is Hs equals ks cubed slash s cubed plus a2s caret 2 plus a1s plus a0. Let's break this down. The k at the beginning is the passband gain. This is simply how much the signal is amplified or attenuated in the frequency range where the filter is designed to pass signals. Often, k is set to 1 for unity gain. Now, look at the numerator, s cubed. This term is crucial for a high-pass filter. As the frequency, s, approaches 0, s cubed also approaches 0. This means the filter's output gain approaches 0 for very low frequencies, effectively blocking them. As frequency increases, s cubed grows, allowing high frequencies to pass through with increasing gain until it reaches the passband gain k. The power of s, which is 3 in this case, directly indicates the filter's order. Next, consider the denominator, s cubed plus a2s caret 2 plus a1s plus a0. This is a third-order polynomial. The roots of this polynomial are called the poles of the transfer function. The location of these poles in the complex plane determines the filter's specific frequency response shape, its stability, and its cutoff frequency. The coefficients a0, a1, and a2 are very important. They define the filter's characteristics. For instance, they determine if it's a Butterworth, Chebyshev, or Bessel filter. Each type has different trade-offs in terms of flatness in the passband and steepness of the roll-off. These coefficients also incorporate the filter's cutoff frequency, omega c. The cutoff frequency is the point where the filter's output power is half of its passband power, or where the gain drops by 3 decibels. For a high-pass filter, frequencies above omega c are generally passed, and frequencies below omega c are attenuated significantly. So, in summary, the transfer function Hs provides a complete mathematical description of how a third-order high-pass filter processes signals, from blocking low frequencies with its s-cubed numerator to shaping the transition band and passband with its complex polynomial denominator and coefficients. Thank you for joining me on this exploration of third-order high-pass filter transfer functions. I hope this explanation was clear and helpful. If you found this video useful, please consider giving it a thumbs up. Don't forget to subscribe for more insights into electronics and signal processing. See you next time.